Hi everyone, my name is Adam Holmes. I'm a graduate student with the University of Chicago, as well as a research scientist with Intel Labs. Today I'll be discussing some of our work amplifying the quantum computing power of near-term quantum devices using techniques derived from quantum error correction. This work is a collaboration between the EPIC expedition in computing, the University of Chicago, the University of Southern California, Intel, and others. Our work is also available on arXiv at this identifier here. One of the key messages we want you to take away from this work is that there are these pre-existing regimes of quantum computers sort of in the literature. We typically carve out the design space into the near-term devices, or the noisy intermediate scale quantum devices. Those typically have a low quantum volume or a low ability to perform quantum computation. And then we separate those as distinct from the fault-tolerant quantum computers of the future, which will use fully-fledged quantum error correction techniques and be characterized by a high quantum volume. NISQ plus is a region that we've sort of defined in this work as sort of in the center, where we've taken sort of a smaller, more intermediate scale quantum device and added in some components of fault-tolerant quantum computing, but are not doing fully-fledged or fully accurate error correction or error detection. And what we're shown here is that we can actually boost the quantum volume of our near-term devices by doing this sort of approximate fault-tolerant mechanisms. Specifically what I mean by this is if you look at a metric like the simple quantum volume, where you're taking the number of qubits on a device and you're multiplying it by the number of gates you can perform per qubit, you can see here that for the NISQ targets in pink or red, you see simple quantum volumes that are denoted by the area of these rectangles. And those are compared to these blue rectangles, which are showing the NISQ plus devices, or devices that we've used approximate error detection techniques to amplify. And you see a several order of magnitude difference in terms of compute volume. And the reason for this is that what we've done is we've effectively taken and reduced the number of qubits on the device by encoding logical qubits out of them, but we gain several orders of magnitude in terms of the number of gates we can perform per qubit, per logical qubit, because we've made those logical qubits much more robust. And we'll quantify a little bit more specifically how that affects applications at the end of this presentation. So this talk will first give a quick background and motivation about quantum error detection, quantum error correction as it relates to our work. Then we'll go through the implementation of our techniques in SFQ hardware and the algorithms we use. And then we'll talk about the results, and we'll do some quantification of our performance. So first, to the background and motivation. I'm going to just lightly go through what techniques are used in quantum error detection. What we're assuming here is an execution model where we have a two-dimensional rectilinear grid of qubits on our quantum device. Those qubits have been bipartitioned into two sets, one set being the data qubits, or actually holding the information that we're using to compute, and the other set are denoted as error qubits or error syndrome qubits. These qubits are performing error parity checks among all of the four neighbors of data qubits that each one is adjacent to, and is reporting back any parity change in the errors. You can think about this just as a regular classical repetition style code, where you're looking at the parity between different sets of errors. So the execution of an algorithm then is characterized by a periodic cycle where each cycle measures all of the error qubits on the device and extracts all of the signals or hot syndromes where error qubits are reporting back a parity change. And then the error detection problem is to take these hot syndromes and to decode back what series of data qubit errors is most likely to have caused that sequence of error syndromes. An example of this is shown in the bottom of this image, where we have three red data qubits, or data qubits that have had errors occur. The syndromes reported back from that measurement pattern are only hot for the second and last error qubit on that particular pattern, because those are the only two that have odd parity checks being returned. The two error qubits in the center of this device actually don't return any parity check back because their error parity has remained constant even in spite of the errors occurring. So that's the error detection problem. We're taking these hot syndrome patterns and trying to figure out which pattern of data qubit errors is most likely to have caused that. One of the major problems in systems that implement this type of error detection is what's called the decoding backlog. So as a quantum algorithm is executing, when the algorithm hits an operation, the quantum system has to fully comprehend the state of errors on the device before it can correctly execute that operation. So because of this, latency begins to accumulate if the rate of error syndrome generation exceeds the rate of syndrome processing by your decoder. And in fact, this leads to an exponential accumulation of overhead, exponential in the number of operations in your algorithm. So the point here is that even slightly slow decoders can actually make applications take exponentially long to complete, therefore really nullifying the reason that we were trying to use the quantum computer to perform this computation in the first place, right? So we take this problem seriously, and we try to design a technique to reduce that ratio, reduce the syndrome processing ratio, or the rate of syndrome generation divided by the rate of syndrome processing. To compare this or situate it in context with prior work, we took a look at just sort of doing some bookkeeping, how prior decoders perform with respect to a bunch of quantum arithmetic applications. And what we see is that most of these decoders are sitting around a 1.9 or a factor of 2 in syndrome data processing ratio. Which, while at the surface that may seem like it's not a very large issue, given that the depth of these quantum arithmetic circuits is pretty high, we can see that even for those low, factor of 2 syndrome data processing ratios, we quickly build out to, really intractable algorithm execution times. So this is a problem in sort of the existing decoder techniques. Our alternative approach is instead to do decoding as fast as we can, with the sacrifice that some of our solutions to our decoding problem will not be exactly correct. So with that approximation, we're going to be able to speed up the algorithm, and we're going to be able to print it into an ASIC that's going to be co-located with the quantum device inside a dilution fridge. So by nullifying out the latency required to communicate back and forth to the classical device, as well as by approximating the error detection algorithm so that you can speed it up, we see that our decoder actually sits well below a syndrome processing ratio of 1. We're sitting at about 0.125. And so that's actually a big crux of where we're gaining a lot of our power from. So now I'm going to talk a little bit about our specific circuits and our implementation details. So I'm going to talk about our decoding technique using SFQ, or single-flux quantum logic. The idea is we are going to print an ASIC implementing an approximate decoding algorithm inside the fridge. So our goal was to build out an ASIC that we can co-locate inside a dilution fridge at cryogenic temperatures with a quantum device, making use of properties of the SFQ logic, like 2 properties in particular. SFQ can typically be clocked at extremely high speeds, and it dissipates very low power. Because of that, it makes it a great candidate for printing an ASIC that can actually be located within the temperature region of a quantum device, within the same region as the quantum device itself, inside a dilution fridge. The main problem with doing this is that SFQ implementations of complex logic typically take very large amounts of area. They have very large area footprints. So what we needed to do was we needed to take a look and re-evaluate the decoding algorithm such that it becomes an approximation that allows it to be efficiently synthesizable in terms of area in SFQ, but we don't sacrifice too much accuracy in terms of decoding performance. And so we did this by effectively approximating regular decoding algorithms, as we'll show here next. So our approximate SFQ-based decoding algorithm is inspired by the union find algorithm. So this algorithm operates by basically on a grid. Effectively, you can use it as a search algorithm, where if you have point A and point B on a grid, you're going to grow clusters of nodes that you're searching through, originating at each one of the points that you're searching between. And then once those clusters intersect, you've now found a path between those 2 points. We use that technique and we print that into the ASIC implementing our decoding algorithm. So here what I'm showing is actually a grid of SFQ ASIC modules, pitch matched as close as possible to the actual physical qubits. So in step 1, I'm showing 2 hot syndromes, or 2 error qubits that have been measured, or that are reporting parity errors. Those correspond directly to underlying data measurement qubits that are sitting underneath the SFQ modules. In step 2, pair signals, or signals, are sent out 1 step in every direction to the neighboring SFQ modules. And these constitute the clusters that are going to be used for searching. So these grow throughout a number of steps, and here in step 3, we see the first cluster intersection occurring at that bottom right and top left intersection points. So what we do at that point is we arbitrarily break that tie, and we choose the bottom right-hand pathway, and then we report that back in step 5, and we clear the board in step 6. Our final design makes use of 3 additional mechanisms accounting for basically resetting these clusters so that we don't match to things that are too far away and don't report multiple matches as well. Boundaries, where we're actually matching to the boundaries if those things are closest, and tie breaking, or equidistant path breaking mechanisms, where we're going to break ties in terms of degenerate sets of paths that could all be equally likely. So I'm going to describe those 3 mechanisms in a little bit more detail. Here, what we're showing is, on the left, baseline mechanism without any of these 3 mechanisms. And on this board, we have shown there's 4 hot syndromes lit up in the sort of gold diagonals. And the purple chains are the ones chosen by the decoder without any ability to reset the cluster growth. So you'll see after step 1 that the nearest neighbor hot syndromes, the tops and the bottoms, will pair together. But without the ability to sort of stop the search early or reset the clusters, the search is going to continue, and you will actually pair up all of these together. So we don't want to do that, and we added a mechanism to clear the reset or reset the clusters once paths have been found. Next, in the center, we added, this is a solution that added resets but does not have boundaries accounted for yet. And so in this example, there are 2 hot syndromes on the board, but our decoder decided to pair them together because there was no ability to pair to the boundaries, even though the distance between the hot syndromes and the boundaries makes the boundary match an actual higher likelihood solution than matching to each other. So we accounted for that as well. And lastly, we accounted for tie breaking, where here we have 3 hot syndromes on the board and 4 different paths that are all equally likely. We added this request grant kind of communication mechanism between the modules so that whenever a module wants to pair with another, there has to be this handshake that occurs between those modules so that we only report back the correct number of paths. All right, so I'm going to talk more now about our results. First is the holy grail of metrics for error correction performance is what's called the logical error rate. So this is a plot of the physical error rate of the device, or how often each physical qubit is going to incur errors, and the logical error rate of the device, meaning after encoding into logical qubits, how often do those logical qubits experience errors? An accuracy threshold is this point on this plot where it becomes beneficial to add more qubits into your encoding. to increase the code distance of your encoding. So here we're showing code distances 3, 5, 7, and 9. And so increasing that number just means we're using more physical qubits per logical qubit, and with the goal that the more physical qubits we use, the better the system gets, the lower the logical error rate we'll experience. An accuracy threshold is the point on that graph where we see that begin to happen. So here at right about 5 physical error rate percentage, we see a transition where after that point, or for lower physical error rates than that, we begin to see exponential separation between code distances in terms of logical error rate. So increasing from distance 5 to distance 7 begins to give you a benefit below the 5% error rate threshold, whereas above it doesn't. The actual change in performance from increasing your encoding distance actually washes out. So we see an accuracy threshold at approximately the 5% physical error rate. And this is actually comparable to some other techniques. The next thing I want to highlight is that we can take a look at how well we're doing in terms of speed and accuracy together and compare this to other decoders. So this plot is a resource requirement plot where it says, okay, if your physical system has this error rate, and for a fixed algorithm size, what is the code distance required to perform all the operations in that algorithm correctly without expecting any errors to occur? This plot actually accounts for the decoder backlog that we talked about earlier. And what will happen is, because the decoder backlog builds up in some of these cases, that extra time will contribute to needing to protect your qubits for longer periods of time, which means you're going to need a higher code distance as well. So even though there are more accurate decoding algorithms that are being used in these other decoders, the backlog building up contributes heavily to basically requiring more resources from those decoders. What we see here at the bottom is minimum weight perfect matching, which is the canonical algorithm for solving this matching problem for the decoding algorithm without backlog. So if we could just run an ideal algorithm, that's the resource requirements you would need to perform this particular algorithm or this particular quantum computation. We see in the blue, which is our decoder, a resource requirement that is much closer to optimal than any of these other decoders for physical error rate regimes that stay below about the 5% range. Again, that was because that was our accuracy threshold. These other decoders actually have higher accuracy thresholds. So, we compared specifically to a software-defined union-find algorithm, a neural network-based decoding algorithm, and minimum weight perfect matching in software with a backlog. And all of those do have higher thresholds, so they can deal with the physical error rates that are higher than we can. However, once we enter a regime where the SFQ decoder can perform decoding effectively, then we see up to an order of magnitude of difference in terms of the resource requirements to perform this particular computation. Lastly, we took a look at the synthesis results of our decoder. And so these are reported values for each one of those SFQ modules, sitting above pitch matched as close as possible to physical qubits. We see here that our full circuit has a logical depth of 6, which in SFQ clock speeds corresponds to a latency of about 163 picoseconds. We were shooting for about a square millimeter in total area, and we got to about 1.3 square millimeters. So we're pretty close to pitch matched. We would like to reduce that in future work, but as it is now, it is pretty close, and we're pretty happy with that result. In terms of power consumption, again, SFQ dissipates very low power, and so 13 microwatts is a very enabling number that allows us to pack many of these modules inside the typical cryogenic cooling system budget. All right, so with that, I would like to sort of just summarize. In the future, actually, as we build out these quantum computers, it's really vital to perform as much computation as you can on them. And many of the design decisions that go into these near-term computers are going to be enabling or prohibitive of that amount of computation. There are many factors basically outside of just the fragility or the error rates of the physical qubits themselves. And in order to show as soon as possible that these quantum devices will have, a quantum speedup or a quantum advantage, it's important to make those design decisions to amplify their quantum volume. We propose to do this with an approximate error detection algorithm printed in SFQ-based ASICs. And we show that by doing this, we can actually expand the quantum volume of these near-term machines by many orders of magnitude. So with that, I would like to wrap up and just say thank you very much for your time. Our work is available on archive and will be available again, through the conference. We'd like to acknowledge once again the collaboration. The funding acknowledgements are here as well, and we'd like to thank our colleague Jonathan Baker as well for helpful conversations and for providing our arithmetic benchmarks. Thank you very much for your time. Stay healthy, stay safe, and bye for now.